Hello Math Study students. In this video we're going to take a look at the characteristics of a normal distribution of data. So let's start with an example. We have Pedro who measured the height in meters of 150 trees in an apple orchard and drew a diagram to represent the frequencies of the heights of the trees. So here's a diagram of his data. Now notice that this is just says frequency. It does not say cumulative frequency. All this is it's just an indication of for every height of tree, he just graphed how many trees had that particular height. So this is not a cumulative frequency graph. Those graphs would have a shape like this. This is different. This is where we're just graphing how many trees had a particular height. And so when he graphed that, notice that the data took on this shape. This shape is called a normal distribution. So I wonder if you could think of some other examples of data events that would have a distribution like this one. Some examples I'm thinking of are maybe SAT scores. If we were to graph everyone's SAT scores in the country, it might take on a normal distribution. Or maybe if we were to record the heights of all the juniors at Garland High School, okay, it's likely that we'd have a whole lot of people that have an average height in the middle, and then a few that were really short and a few that were really tall. It would take on this normal distribution. Or maybe the lifespan of some electronic, like a light bulb or something. So the lifespan of light bulbs. Okay, some light bulbs might last a really long time. Some might last a really short time, but the majority of them are going to fall somewhere in the middle here, their lifespans. So you could probably think of some other examples of events that his data would take on a normal distribution. Let's go ahead now and take a look at the properties of a normal distribution. And so here's a good example of a normal distribution. First of all, the data will take on the shape, you've probably heard this before, it'll take on the shape of a bell-shaped curve. It kind of looks like an upside-down bell. The data will also be symmetrical about the mean. Okay, I'm going to use mu for mean. Let me just go ahead and write down what that represents. It says mean. I hope you can read that. Okay, so in other words, it's very symmetrical data. The mean and the mode and the median would all be about the same amount. Okay, this is important too. The x-axis, okay, if you take a look at our bell-shaped curve, here's the x-axis. The x-axis serves as an asymptote for the, bell-shaped curve. Okay, so what that means is, as we look at the graph of the data, on either end, the data will get closer and closer and closer and closer and closer to that x-axis without actually touching it. Okay, an asymptote acts as a boundary for a graph, where a graph gets closer and closer and closer and closer to it, but never actually gets there. The total area under the curve would be equal to 1, or I keep grabbing the wrong pen, sorry about that. 1, or in other words, 100% would be the area if we looked at the total area under the curve. I think it's pretty obvious as you look at the diagram that 50% of the area would be to the left of the mean and 50% of the area would be to the right of the mean. That's what gives it that bell-shaped curve. Okay. Approximately, and then this might be new to you, approximately 68% of the area is within 1 standard deviation of the mean. So if you take a look at the graph, here's our mean. Okay, remember we use a lowercase sigma to represent standard deviation. So if you look at the area of the graph that would be from 1 standard deviation below the mean to 1 standard deviation above the mean, that's going to be 68% of the data. And then approximately 95%, so, oops, I forgot, didn't finish my percent symbol. 95% of the area is going to be within 2 standard deviations. So again, if you take a look at the graph, okay, if we go from 2 standard deviations below the mean to 2 standard deviations above the mean, that's going to be made up of 95% of the area under the curve. And then finally, approximately 99%, so that's almost all of your data, would be within 3 standard deviations of the mean. So again, taking a look at the graph, here's your mean. So if we go from 3 standard deviations below the mean to 3 standard deviations above the mean, that's going to be 99% of your data. So you have very few, very, very small amounts of data that would be more than 3 standard deviations above or below the mean. So let's take a look at example 1 that says the mean mu of the heights of the trees in Pedro's orchard is 4 meters and the standard deviation sigma is 0.5 meters. If the height of an apple tree is x, find the following. So let's find the probability that the apple tree is less than 4 meters. So we're going to write that probability like this. Let's just say the probability of, remember x is the height of the tree, so the probability that x is less than 4 meters would be 50%. Whoops. 50%, because as you look at the graph, remember that the median, not the median, the mean is 4, and 50% of the area under the curve would be to the left of the mean. So the probability of the height of the tree being less than 4 would be 50%. Letter B says, find the probability that an apple tree is less than 4.5 meters. So let's write that probability like this. The probability that x, being the height of the tree, is less than 4.5 meters. Well, if you remember, 0.5 was the standard deviation for the heights of the tree. So if you take a look at the graph, 4.5 meters would be half of the area plus 1 standard deviation. And remember, 1 standard deviation is 34% of the area under the curve. So the probability of the tree being less than 4.5 meters would be 50% plus that extra 34%, that first standard deviation above the mean. So that would be equal to 84%, or if we were to write that as a decimal, it would be 0.84. Okay, and then the next example says, or the next thing says, let's learn how to find expected value. An expected value is what we get when we multiply the number in the sample by the probability. So like in this example, if we choose 100 apple trees at random, find the expected number of trees that would be less than 4 meters. Well, remember we saw up here that the probability of a tree being less than 4 meters was 50%. So we just take the number of trees, which is 100, and we multiply it by that probability, which is 0.5 or 0.5. So that's going to be 50 apple trees. Okay, so apple trees. So the expected value of how many trees would be less than 4 meters would be 50 apple trees. Example 3 says, if we choose 100 apple trees at random, find the expected number of trees that would be less than 4.5. So we found that probability up here. The probability of a tree being less than 4.5 was 84%. So we'll take those 100 trees and multiply it by the probability of being less than 4.5 meters, and that turns out to be 84 apple trees. So let's take a look at example 4 that says, the waiting times for an elevator are normally distributed with a mean of 1.5 minutes and a standard deviation of 20 seconds. So one thing I'm noticing right off the bat, notice that our mean is given in minutes and standard deviation in seconds. So we'll want to pay attention to that in a minute as we start working on this problem. So letter A says, sketch a normal distribution diagram to illustrate this information, indicating clearly the mean and the times from 1, 2, and 3 standard deviations of the mean. So to get that bell-shaped curve, here's how we might want to go about drawing this diagram. So this is letter A. I'm going to go ahead and label my horizontal axis. We're going to measure time on that horizontal axis. And let's go ahead and convert everything to seconds. I think that's going to make it a little bit easier. So if we go back to the information given, the mean was 1.5 minutes. That's 1.5 minutes. So that's a total of, let's make a note, that's a total of 90 seconds. Oops, got the wrong pen again. Okay, that's a total of 90 seconds. Okay, so 90 seconds is our mean. So what I like to do is just draw a dotted line to represent the mean, which would be 90 seconds. And then let's go one standard deviation to the left and to the right. And then a second standard deviation to the left and to the right. And then that third standard deviation to the left or the right. And then what we can do is just sketch a curve that goes right along there and kind of gets that bell shape for you. Okay, so then let's label. Remember, the mean was 90 seconds, okay? And if our standard deviation is 20 seconds, then one standard deviation below the mean would be 90 minus 20, or 70. And then one standard deviation above the mean would be 90 plus 20, or 110. And then two standard deviations below would be 50. Two standard deviations above would be 130, and then three standard deviations below would be 30, and three standard deviations above the mean would be 150. So let's go ahead and indicate that 90 seconds was our mean. 110 seconds would be our mean plus one standard deviation. 130 would be the mean plus two standard deviations, and then 150 is the mean plus three standard deviations. Oops. And then going in the other direction, 70 would be the mean minus one standard deviation, 50 is the mean minus two standard deviations, and 30 is the mean minus three standard deviations. So that takes care of letter A. Let's take a look at letter B. That says, find the probability that a person waits longer than 2 minutes 10 seconds for the elevator. So first of all, let's go ahead and convert that time into seconds. So 2 minutes and 10 seconds. 2 minutes is 120 seconds plus 10 more. That would be a total of 130 seconds. Okay. So for letter B, let's go ahead and let's let X represent the number of seconds that a person waits. So number of seconds waiting. Okay, so what we're asked to find in letter B is the probability that a person is waiting more than 130 seconds. So to find that out, let's write a breakdown of how much area is in each of these sections that are sectioned off by the standard deviations. So remember, this middle section was 68% of the area. So let's go ahead and label on either side of the mean. This section would be 34%, and then this section would be 34%, okay? And then if from, let's see, from two standard deviations below to two standard deviations above, that's a total of 95%. So if we subtract 68% and then divide that by 2, that means that this is, let's see, 13.5% of the area and 13.5% of the area over here. And then lastly, remember, from 3 standard deviations below the mean to 3 standard deviations above the mean, that's 99%. So if we take 99% and subtract all of this, that would leave us with 4%. So if we split that on either end, then we've got 2% here and 2% here. Okay, so back to our problem. We're trying to find the probability that a person waits longer than 130 degrees. Not 130 degrees, 130 seconds. So we're talking about this area of the curve. So if we look at the right half of the graph, now remember, from the mean all the way to the right, that's 50% of the data. So if we take 50% of the data and we subtract this total of 47.5%, that's going to leave us with this area to the right. That would be the area of the curve, the area that represents the number of people that wait more than 130 seconds. So we're going to take 50%, that right half of the curve. Oops, I keep grabbing the wrong pen. Okay, 50%. And we're going to subtract 47.5%. Again, that 47.5% would be this part of the curve, 34 plus 13.5. That would leave us with this area. And that gives us 2.5%. So that's the probability that a person is going to wait longer than 130 seconds for the elevator. Then letter C says, find the probability that a person waits less than 1 minute and 10 seconds for the elevator. So 1 minute and 10 seconds, that's 60 seconds plus 10 seconds. So that would be 70 seconds. Okay, so for letter C, let's find the probability that a person, remember X was the time a person waits for the elevator, that X is less than 70 degrees. Okay, so if you take a look at the graph, we're going to find out what this area represents, okay, to the left of 70 degrees. So if we look at the right half of the data, remember the right half is a total of 50%. So we'll take 50% and subtract this 34%, and that's going to leave us with this area, which represents the amount of people that, or the number of people that would wait less than 70%. Or not the amount, it'd be the probability. So we're going to take 50%, and we're going to subtract that 34%. Okay, again, we're taking this whole right half of the bell-shaped curve, we're subtracting this much of it, and that will leave us with the probability of a person waiting less than 70 seconds for the elevator. So that turns out to be, let's see, 50 minus 34 is 16%. All right, and then letter D says 200 people are observed and the length of the time they wait for the elevator is noted. Calculate the number of people, so this is an expected value, the number of people expected to wait less than 50 seconds for the elevator. So the first thing we need to do is get that probability of a person waiting less than 50 seconds. So we'll write it like this. We'll say the probability of X being less than 50. So if you take a look at the graph, okay, less than 50 is this much of the graph, right? So if we take 50%, if we take the left half and subtract all of this, which is a total of 47.5%, so 50% minus 47.5%, that's going to leave us with 2.5%. That's the probability of a person waiting less than 50 seconds for the elevator. So to find the expected value, remember there were 200 people observed waiting for the elevator. To find the expected value of how many people will actually wait less than 50 seconds, we take that 200, the number of people, and we multiply it by the probability. I'm going to put that in decimal form, so it would be 0.025. So that's a total of 5 people. It would be the expected number of people that wait less than 50 seconds for the elevator. Example 5 says, the heights of 250 20-year-old women are normally distributed with a mean of 1.6 meters and a standard deviation of 0.06 meters. So the first thing I notice on this one is that our mean and standard deviation have the same units this time, so we're not going to have to do any conversions. Letter A says, sketch a normal distribution diagram to illustrate this information, indicating clearly the mean and the heights within 1, 2, and 3 standard deviations of the mean. So then for letter A, okay, let's go ahead and let our horizontal axis is going to measure height. This is a height of 20-year-old women in meters. So this is going to be height in meters. Okay. And then let's just go ahead and indicate our mean, and then 1, 2, and 3 standard deviations on both sides. Okay, so I'm just going to sketch a nice bell-shaped curve. Whoops. Okay, that kind of looks like a bell. Okay. Where, remember our mean was 1.6 meters, so let's go ahead and label that. Oops, it's 1.68 meters. Okay, 1.68 meters. And then if we go 1 standard deviation below the mean, well, our standard deviation is 0.06. So I'm going to take 1.68 and I'm going to subtract 0.06, and that gives me 1.62. So 1.62 is one standard deviation below the mean. And then if I subtract another 0.06, we're going to get 1.56 for two standard deviations below the mean, and then subtract another 0.06 and we get 1.50. And then let's do the same thing in the other direction, but this time we're going to add a standard deviation. So 1.68 plus 0.06 is 1.74 meters. And then let's add another 0.06, and that would be 1.80. And another 0.06 would be 1.86. All right? So here is our mean of 1.68. Then this is one standard deviation below the mean. Here's two standard deviations below the mean, and then three standard deviations below the mean. And then the same thing in the other direction, only this time we're going to be above the mean. So this is one standard deviation above the mean, oops, and then two standard deviations above the mean, and then finally three standard deviations above the mean. All right, so I think we've taken care of letter A, so let's move on to letter B. Letter B says, find the probability that a woman has a height between 1.56 and 1.74 meters. So let's let X represent the height of a woman in meters. So it would be the height in number of meters. Okay, so what we're being asked to find in letter B is the probability that a person is between, that height falls between 1.56 and 1.74 meters. So what we're being asked actually here is, what is the probability that a person's height is from two standard deviations below the mean to one standard deviation above the mean? So remember, if we look at this area that goes from one standard deviation below to one standard deviation above, that's 68% of the data. And then this would be another 13.5% of the data. So the probability of a person's height, a woman's height, being between 1.56 and 1.74 meters would be 68% plus that additional 13.5%, which totals 81.5%. So there's an 81.5% chance that a woman's would have a height between 1.56 and 1.74. All right, and then letter C says, find the expected number of women with a height greater than 1.8. Okay, so the first thing we need to do is find the probability that a woman has a height more than 1.8. So that would be this area of the curve. So if we look at just the right half of the data, which represents 50% of the data, if we take 50% and subtract this area, which remember was 34% plus 13.5%, so this is a total of 47.5%. To find that probability, let's go ahead and write it down. Okay, the probability of a height being greater than 1.8 meters is going to be 50% minus 47.5%, which is 2.5%. So there's only a 2.5% likelihood or chance or probability that a woman's height is greater than 1.8. So to find the expected number, remember we were told at the beginning that there were 250 women that were measured. So to find the expected number of women with a height greater than 1.8, we'll take 250 times this probability. So that's going to be 250 times, I'm going to write the percent in decimal form, 0.025. And then that turns out to be 6.25. Well, we're not going to have a fourth of a woman, so let's just go ahead and round down and say that there would be 6 women. It's expected that there would be 6 women out of 250 who have a height greater than 1.8 meters. The rest of the examples that we'll do in these notes will all be calculator problems. So rather than drawing a normal distribution graph and answering questions based on the graph, we'll be using the calculator. Now I know you don't have a calculator in your hands right now, but tomorrow in class you'll get a chance to practice. So what I've done is I've just written down the instructions for what to do on the calculator, so tomorrow you'll be able to practice in class. So let's take a look at this first example. Example 6 says, the lifetime of a light bulb is normally distributed with a mean of 2,800 hours and a standard deviation of 450 hours. So the first question is, find the percentage of light bulbs that have a lifetime of less than 1,950 hours. So again, we're not going to draw a graph and look at a graph this time. We'll use the calculator. So for letter A, I've written the steps that you're going to follow to answer this question. So the first thing you'll do is hit the menu button. So hit the menu button, then choose number 5 for probability. We're doing probability this time. And then choose number 5 for distributions. And then choose number 2. Now this is the Inspire's way of saying a normal distribution. So it says normal CDF. That means normal distribution. So when you do that, you'll have a screen that's going to ask you for some entries. So all you have to do is enter what it's asking for. So the first thing we're going to type in is a lower bound. Now remember what we're finding. We're finding the percentage of light bulbs that have a lifetime of less than 1,950 hours. So what you're going to type in here is actually, this is the calculator version of scientific notation or standard form. So what this is a very, very small number. It's a calculator way of typing in a very, very small number. So you might be wondering, why don't we just put a 0 here? Well, the reason why is, remember what we said about a bell-shaped curve. Let me find a space to draw one. Remember, a bell-shaped curve has the x-axis as an asymptote. So that means on the left end of the graph gets closer and closer and closer and closer and closer to the x-axis, but never touches it. So this graph will never get to 0. So that's why we put, instead of putting 0 for the lower bound, we want to put an extremely small number, and that's what this represents. Now, one note, when you type this in, you'll type in -9, and then there's an EE button. It's right to the left of the A key, and that's what you type in for E. So you'll hit -9 and then hit that EE button and then type 999. And that represents your lower bound, and it's an extremely small number. And then for the upper bound, we're going to put 1,950 because we were trying to find the percentage of light bulbs that have a lifetime less than 1,950. So you'll type that in. Then the next thing the calculator will ask for will be the mean, which we were given, and the standard deviation, which you're given. So you'll just type that all in, and it'll give you the answer. So the probability of, let's go ahead, let's let X represent the lifetime of the bulb in hours. Okay, so what we're being asked to find is the probability that X is less than 1,950. So what you'll do is you'll type all this information into the calculator, and it will give you an answer of 0.2, nope, that's not right. Hold on, let me fix that. It's 0.0295, or if we were going to write that in percent form, it would be 2.95%. Both of those answers would be correct. Okay, and then letter B says, let's find the percentage of light bulbs that have a lifetime between 2,300 and 3,500. Okay, so this time, instead of our lower bound being almost virtually 0, we're going to have a left bound and we're going to have a right bound. So you'll hit menu again, choose 5 for probability, 5 for distributions, 2 for a normal distribution, and then you'll type in, the calculator will prompt you for a lower bound. That's where you'll type the 2,300, and then it'll prompt you for an upper bound. That's where you'll type in 3,500, put the same mean and the same standard deviation. So our probability that the bulb lasts between 2,300 and 3,500 hours. Calculator will give you the following answer, 0.0807 or that's going to be 80.7%. All right? And then letter C says, find the probability that a light bulb has a lifetime of more than 3,800 hours. So that means we'd have a lower bound of 3,800, and then the upper bound is going to be a very, very, very large number. Again, remember this graph gets closer and closer and closer to the x-axis, but never touches it. So that's why you'll type in, again, choose menu, then 5 for probability, 5 for distributions, 2 for normal distribution, and then you'll type 3,800 for a lower bound, and type in 9, and then find that EE button next to the A button, and then type 999. That's a calculator way of saying an extremely large number for your upper bound. Same mean, same standard deviation. So the probability of X being greater than the number of hours the bulb lasts being greater than 3,800, the calculator will tell you is 0.0131, or if you can write that as a percent, it would be 1.31%. Okay? And then letter D says, suppose 120 bulbs were tested. Find the expected number of bulbs with a lifetime of less than 2,000 hours. So the first thing we have to do is find the probability that a bulb lasts less than 200 hours. Okay, so that's the probability of X being less than 2,000. So to find that probability, okay, here's what you'll type in your calculator. Hit the menu button, then 5 for probability, 5 for distributions, 2 for a normal distribution, and then type your lower bound. We're less than 2,000, so your lower bound is an extremely small number, very, very, very close to, but not equal to 0. Your upper bound is 2,000, the same mean, the same standard deviation, and you'll get a probability of 0.0377, or in percent form, that would be 3.77%. Now, that's not the answer to the question. Remember, the question was, find the expected number of light bulbs out of 120 that have a lifetime less than 2,000 hours. So to get that expected value, we need to take our probability and multiply it by the number of bulbs. So we're going to take 200, change the color here, 200 times the probability of 0.0377, and the result is 4.53, but we're talking light bulbs. You're not going to have half of a light bulb, so you could say either 4 or 5 light bulbs. Light bulbs. I can barely fit it in there. There we go. There's our answer. This next example, example 7, we're going to use what's called an inverse normal calculation. And you'll see how this is an inverse, how it's working backwards. Let's take a look at the example. It says the volume of cartons of milk is normally distributed with a mean of 995 milliliters and a standard deviation of 5 milliliters. It is known that 10% of the cartons have a volume less than X milliliters, so we're going to use an inverse normal calculation to find the value of X. So this time we know that there's a 10% probability that a carton would have, let's see, less than X milliliters. We just don't know how many milliliters that is. So if you can, I guess we could make a quick sketch here. If you think of that normal curve, okay, here is 10%. Okay, there's 10%, there's a 10% probability that there's less than 5 milliliters, or I'm sorry, not 5, we don't know what it is. Let me erase that. Less than X milliliters, so we need to find that number of milliliters. So we'll use the calculator to do that, and here are the steps. You'll hit the menu button, choose 5 for probability, 5 for distributions, but this time you're going to choose 3 for an inverse normal. Okay, and you'll type in the following. The first thing it'll ask for is the area under the curve. Well, we're trying to find, we're told that it is known that 10% of the cartons have a volume less than X milliliters. So that area is 10%, and that's in percent form, so you'll type it in decimal form, so you'll type in 0.10. And then we're told that the calculator will prompt you for the mean and the standard deviation. You're given that information in the problem, so you'll just type that in and the calculator will give you an answer of 998.59. So x is equal to 988.59. Let's go ahead and change that to 3 significant figures. So that would be approximately 989 milliliters. Okay, so 10% of the cartons have fewer than 989 milliliters. Let's take a look at one more calculator example. Example 8 says, the weights of pears are normally distributed with a mean of 110 grams and a standard deviation of 8 grams. So letter A says, find the percentage of pears that weigh between 100 grams and 130 grams. So in other words, this is asking what's the probability that a pear weighs between these two weights. So grab your calculator, you'll choose the menu button, choose 5 for probability again, 5 for distributions, and then 2 for a normal distribution, and then you'll be prompted for these amounts. So our lower bound is going to be 100 grams, so that's what you'll type in, 100 grams, okay? And then the upper bound is 130 grams. And then we're told in the problem that the mean is 110 and the standard deviation is 8. So you'll type in 110 and 8 for those two amounts. And the calculator will give you an answer. Now, what were we finding? We were being asked to find the probability that, let's let X represent the weight of the pear. So the weight of the pear, and that's in grams, so the number of grams. Okay, so that would be the probability that X, that weight of the pear, is between 100 and 130. Okay, and the calculator will give you the answer of 0.888, or in percent form that would be 88.8%. All right, and then letter B says it is known that 8% of the pears weigh more than m grams. Find the value of m. Okay, so we're going to use that inverse normal distribution function on your calculator again, but we need to think about this. We need to find if 8% of the pears weigh more than 9%. Let's just sketch a little bell-shaped curve, okay, where we have 8% of the pears weigh more than m grams. Well, let me change this a little bit. So this would be m grams, okay? And then 8% weigh 8% weigh more than m grams. That means that you have all of this area that weighs less than m grams. So that would be 92%. So when you go to punch numbers in your calculator, when it comes to area, that's what we need to put in. We need to put 92%. Because if 8% of the pears weigh more than m grams, that means 92% weigh less than m grams. So on your calculator, you'll hit menu, and then 5 for probability, 5 for distributions, 3 for inverse normal distribution, and then for the area, as we said, we'll type in 0.92, that 92% in decimal form, and then the mean was 110 again, standard deviation was 8, and so for letter B, the probability, or it's not the probability, we're finding m, we're finding the number of grams, which is m. So m is equal to, let's see, it's 121.2. So with 3 significant figures, that would be 121 milligrams. All right. And then letter C says 250 pears are weighed, so calculate the expected number of pears that weigh less than 105 grams. Okay, so the first thing we need to do is find the probability that a pear weighs less than 105 grams. So to do that, you'll punch in, hit the menu key, 5 for probability, 5 for distributions, 2 for a normal distribution, and then we need to give a lower bound. Well, our lower bound would be a number that's very, 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 very tiny, that's very close to 0. So that's when you type in 9, hit that EE button, or excuse me, not 9, we need to have to put -9. Let me fix that. We need to put -9 and then the EE button, 999. That represents a very, 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 very tiny number. And then our upper bound, of course, is 105. And then we have the same mean of 110 and the same standard deviation of 8. So that probability turns out to be 0.266 or 26.6%, but that's not the answer to the question. Remember, the question was, out of 250, what's the expected value that would weigh less than 105 grams? So we need to take that 250 and multiply it by the probability of weighing less than 105 grams. So that's 0.266. And that turns out to be 66 or 67 pairs. Either of those answers would be fine because, of course, we wouldn't talk about part of a pair. All right, so we will be doing homework in class next time I see you. If you want, you can go ahead and start the homework. Exercise 5A does not require a calculator, so if you want to get those 4 problems done, you can, or you can just wait and do it in class. And the rest of the problems, you'll need a calculator, so we'll do those in class. So if you have any questions, be sure and ask me then, and I will see you next time.